Okay, good morning, everyone. I want to welcome you to another statistical learning class. Of course, before now, for work you, we started what I call beyond linearity. And of course, we're trying to figure out what is going to be the appropriate function that can be used to model relationship between a predator and a response. And of course, we could look beyond linearity. And of course, when you look beyond linearity and you want to figure out function, okay, that will capture the trend, between two variables. Of course, we have two methods that we can use in estimating such function. One method is parametric, the other one is non-parametric. Now, I remember I walked you through the parametric method. We started by fitting what I call polynomial regression, okay? And of course, the data under investigation was we try to look at the relationship. We're, looking for a function that could adequately describe the relationship between wage and age. And of course, we started by fitting polynomial, okay? And of course, even though we realize polynomial model we perform better than linear regression model, but there's possibility that when you fit a higher degree of polynomial, because of the fact that it's going to be more flexible, there could be some kind of erratic behavior at the edge. And I remember the other time, you saw the problem in the diagram that I show, or probably on Monday. After age 60, you saw what happened. There was a large variance, and a large variance at the age indicate overfeeding. Now, in order to solve a polynomial, in order to solve that problem created, we decided to use an alternative approach that we call step function. And of course, what the step function does is to split or break the continuous predator age into different intervals, being, okay? And initial interval and defeated what I call a constant response function. And of course, I told you disadvantage of that is that disadvantage of that is it's actually going to create discontinuity. Okay, discontinuity. The step function is only be is very useful in a situation where you expect abrupt change or maybe a sudden change. Okay, but situation where you don't expect something like that, the step function is not going to be appropriate. And another thing we think about is can we have a way to combine the knowledge of a step function and you know um, the polynomial, but instead of fitting a global polynomial, okay, we can fit what I call a piecewise polynomial. The piecewise polynomial requires that I need to identify a knot. I need to identify knots. Okay, knot is what I call the cutoff point. I need to identify the cutoff point, and of course, after I identify the cutoff points, and I'm actually going to fit the polynomial, okay, of a certain degree. Maybe I choose polynomial of degree 3, okay, which is cubic. Okay, I fit that to each, you know, um, each interval. But what I show you on Monday and Wednesday is that we experience a kind of a jump, okay? And how do we actually induce continuity? Okay, how do we induce continuity, and how do we also going to benefit from smoothness? Of course, we now use the idea of a spleen, and I discussed two types of a spleen. We have a cubic spleen, you have a natural spleen. Okay, the natural spleen is better. The reason why the natural spleen is better, because with the cubic spleen, okay, there's possibility that at the boundary, when I say the boundary of the knot, okay, the boundary of the knot that you created, you can still have some kind of behavior that is nonsensical, that may be erratic. And what we now want to make that natural, by posing what I call a second derivative, okay, condition on the at the boundary, at the edge, in order to address any kind of erratic behavior at the edge. And what we did, we set the second derivative to 0. Okay, the second derivative determine how rough is the curve. Okay, how rough. Okay, the how rough it is. That is what it determines. So that is all about the parametrical aspect. Now, in the non-parametric aspect, I want to walk you through the non-parametrical aspect now. Now, let me tell you this. The parametric aspect that I just reviewed, whether a global polynomial, whether a step function, whether a piecewise polynomial, whether a cubic spleen or a natural spleen, all of them requires that the functional form should follow a particular, distribution. Does that make sense? So, but in order to induce flexibility, okay, we can decide to say, okay, the functional form does not follow any kind of form. We don't, so if we are not assuming a specific functional form, okay, then we're actually going to have a non-parametric. Now, I want to discuss with you now the non-parametric, the methods in the non-parametric, and I need you to pay attention. Now, in the non-parametric procedure, the way it works, like I said, okay, the non-parametric come with flexibility. Flexibility in terms of we do not have any assumption about the functional form, okay, and not only that, it will enable us to, the locality in the data set, okay, the locality in the data set is guaranteed. Now, when you take a look at what I said here, if the locality, when you are talking about uh, you want it to be localized, then you need a boundary, you need a neighborhood. Does that make sense? And that was why here we said the function f, okay, the way we're going to estimate that, the notion underlying the smoothing is that the value of f at a location x is obtained by considering the values of the observed response y in the neighborhood of s. Let me tell you this. In the neighborhood of a particular, maybe I'm focusing on a particular age, okay? Now, what I'm going to put into consideration, what are the values of the response variable that are within that very age? And that's called the neighborhood. Okay. And that was why I said here, how do we define the neighborhood? I'm going to show you. Then how do we predict response locally? We don't want to predict globally, locally. Okay. And how is smoothness ensured? Because we also need smoothing. I think I defined smoothing the other time. A function is smooth if it varies gradually without any breaks, without any sudden change. Okay, that's what I mean. Okay, now I need you to pay attention. Okay, now what we're actually going to use is what we call kernel smoothing. I need you to pay attention. Kernel smoothing. I'm going to tell you what kernel smoothing does. If you look at kernel smoothing, okay, something that we need to smooth. the function, because that is required. The reason why we move away from global polynomial is because of the fact that there's not going to be smoothness. Okay, we're going to have issue with smoothness. We're going to have issue with with a continuity, because there's going to be a discontinuity. So right now, what we're going to do is we're going to use a kernel smoothing in non-parametric setting. If you take a look at this, I want to make a prediction of age, sorry, of wage. You know, in our data, Y represent wage, X represent age. Now, I want to make a prediction, okay, of wage observing a particular age, but I'm going to use, you know, the wages in the neighborhood of the age that I'm talking about. I'm going to say that again. I'm actually want to make a prediction at a particular point, okay? And I want to pay attention to those data point, okay, for wage that are nearby. And how do I measure the influence of the data point that are nearby? It's what we call bandwidth. Bandwidth. Look at that lambda here. It's what we call bandwidth. And you see, if you take a look at here, what am I talking about? That's a weighted average. Where is the W coming from? The W is from here. Okay. Now the W that is actually the weight. This is what we're using to find the weight. And if you take the lambda is a the bandwidth, and the bandwidth will only tell us how is important those data point that are near, that are that are very close to the age that I'm focusing on. Okay, those ones that are very close, they're going to have a huge weight. Those ones that are far away from that, they're going to have a very small weight. So kernel density function can be used in that regard. And let me tell you this. Uh, when you talk about kernel density function, we have different kind of them. And one of them is this guy, the K. You know, here, take a look at this. You can see there's a K here, right? Okay, which is a K of that, right? Now the K of S is this guy. This guy is what we call Shnikov. There is one of them. We can use a Gaussian. Why do you think we're using them? Because they guarantee look at that continuity. Can you see that? If you see the one for Gaussian, you can see Gaussian. It guarantee continuity, no break. There's no break in the Gaussian. Okay, and the one for that, there's not going to be a break. So we have different kinds of kernel that we can actually use. The essence of the kernel is to the kernel function is to calculate the weight. And let me tell you this, each value of predator will be assigned, okay, a weighted average of the nearby wages. And that function that we're going to use is going to be kernel. I have a paper I'm currently working on that will take me to Columbia, where I've already reparameterized one of the kernel density function for better smoothing. For better smoothing. Okay, now, like I said, we're actually going to have a parameter lambda that we call smoothing parameter, which is the bandwidth, which is the guy, which is the lambda here. Can you see the lambda here? That very lambda is very crucial. The selection of lambda, the selection of bandwidth is very, very crucial, because, you know, we need to strike a balance between interpretability and flexibility when, depending on the values of lambda, it could lead us to a model that may be more interpretable, and it could lead us to a model that may be more flexible. When a model is more flexible, we may not be able to interpret. When a model is more interpretable, it may suffer from smoothness. Does that make sense? So the way we choose lambda, the bandwidth, really matter. Okay, now I'm gonna continue now. And also I said, how do you expect your F curve, the prediction to change as lambda increases? Okay, now, and that is what I'm trying to demonstrate. If lambda increases, if you increase your lambda, it's going to be smooth. Okay, it's actually going to be smooth. But if lambda increases, okay, it becomes smoother and it becomes less flexible. Okay, then the variance will decrease and the bias will increase. Now I want you to pay attention now. Bias will increase. That may not be good. Large value of lambda may not be good when you are seeking an explanatory goal. When you are seeking an explanatory goal, you don't want high bias. You want a low bias. Does that make sense? We are seeking an explanatory goal. But let me also tell you this. Okay, when when the variance go down, okay, I said the variance will decrease and the bias will increase. When bias increase, it is not good for explanation. But when the variance decrease, that may be good for prediction. Does that make sense? That may be good for prediction. Okay, but how are you going to tell? Please, I need you to pay attention. Okay, I'm seeing a lot of projects somebody can embark upon here. I want to, the kernel, the kernel density that I'm actually using here, the one I'm using now, I'm using Gaussian kernel. Don't forget, there are different kernel. Okay, I show you Epachnikov kernel. There's Gaussian kernel. Okay, there's one by me that I've not published, but it's working. I call that exponentiated kernel. Okay, so now, uh, when you take a look at, I decided to now use what I'm presenting right now, okay, is this the choice of bandwidth, lambda. When lambda is 0.5, when lambda is 5, when lambda is 10, I actually want to see how does the selection of bandwidth. What do I call bandwidth? What do I call lambda? Here, I'm talking about how influential are the values of the response that are very close, okay, that are in the neighborhood of the predictor that I'm focusing on. Now, I need you to pay attention. Here, what do you see? Bandwidth equal to 0.5, which means I'm considering a small value. The value of the bandwidth is very small here for 0.5. Okay, what do you see? Look at the red line. Please pay attention to the red line. What do you see in the red line? You see fluctuation, right? So fluctuation here means there's high variance. But even though the bias may be low, but there is high variance. I want you to pay attention to that. So you can see what I call an high variance. And what is the implication of high variance? The high variance actually means your model is going to do a great job with a training data, but you perform poorly with unseen data. Okay, so that is the observation here. So don't forget what I'm doing here. I'm actually using a kernel smoothing. I'm using a Gaussian kernel, and I use a cross validation to be able to come out. You can use a cross validation to come out with the appropriate choice. But what I'm presenting now here is a graphical way. Okay, there are two ways you can look at that. I can look at it graphically. I can use a cross validation. But when you take a look at what I have right now, for when bandwidth is 5, oh my God, it's like this actually filter out the noise. It is smooth. And this particular guy balances trade-off between interpretability and flexibility. But when the bandwidth is 10, okay, when the bandwidth is 10 right now, okay, the other time, what happened here? There is high variance, okay, here, even though this guy achieved low variance, but the smoothness is too high. When you over smooth, when you over smooth, it's actually going to be an issue as well. Okay. So, and that was why I said, okay, this guy here has a low variance. You can achieve low variance with when you have a high values of bandwidth. Okay, low variance. But let me tell you this: there's always a penalty that's going to come when you achieve a low variance. It will come with high bias. Oh my God, it's going to come with high bias. Low variance come with high bias. Now, when you have high bias, oh my God, you will oversimplify the model relationship. It will lead to oversimplification of relationship, because having high bias actually means there could be some potential variable that are missing in the model that actually determine response. So here I said variance, high variance, okay, but what? Low bias, right? Please pay attention. Low bias, high variance here, high variance here, but here, low, low bias. Okay. Now, the one with the high variance is not going to be good for prediction, but may be good for explanation because of the low bias. The one with the low variance will be good for prediction, but may not be good for explanation. But the one with a bandwidth equal to 5 here will strike a balance between bias and the variance. Does that make sense? Okay. Now, any question about but do you know why I said there's a lot of project work here where you can back upon here? Okay. Here I only use a Gaussian kernel. You can decide to use, you can try other kernel, okay, like this guy, you know, a Pachnikov kernel, and investigate your lambda that work too for the same data set. That makes sense? And I told you why we choose all those kernel, because when you look at Gaussian kernel, it's maintained a continuous, you can see that, the curve. That is continuous, right? Okay? If they can look at that too. Okay. Now, I actually going to move right now. I'm done with the first method in the non-parametric. The first method is kernel smoothing. Now, the second method is what we call the local polynomial. And I need you to pay attention. Local polynomials. Oh my God. Local polynomial is more or less like piecewise polynomial in parametric. Okay? There's a piecewise polynomial in parametric. In piecewise polynomial in parametric, we're actually going to have a cutoff point, and you fit polynomial to this and to the other group as well. But in the local polynomial, I'm going to tell you the difference. Now, I said the idea of the local polynomial is similar to kernel that we just did, but instead of a local kernel, a local polynomial is fitted. Now, this is the way it's going to work. We're actually going to feed that local polynomial, okay, over a moving window. It's going to be a moving window. And that very window will slide across your data set. I'm going to say that again. The window will slide across your data set, okay? And then when the window slide across your data set, if you pick on, let's say you pick on it, okay, I'm going to show you, give me 1 second. I'm going to show you this. How how that how that really work. I'm gonna show you how that really work. Okay, I think it is similar to this. Let me just show you this. I need us to pay attention to this. For you to be able to understand the local polynomial, let me go back to the kernel. Pay attention to this. Do you see that this is a plot of y against x, right? I want to show you how the kernel work. If you understand how the kernel smoothing work, you'll be able to understand the local polynomial. Now I plotted y against x. All those dots, they add. This is more or less like a scalar plot, right? Okay. Now, with the kernel smoothing, I'm gonna consider a neighborhood. And when I want to, please pay attention. When I want to consider a neighborhood, I'm going to use a kernel function. It could be Gaussian. A Gaussian is going to be, you know that curve? Whatever all those functions, they look like a curve. And that's why you see this. Look at this. Do you see the pink? Do you see that pink? Then I want to consider some values of y around a particular point s. You see x and x prime, right? I want to consider some values of wages within in the neighborhood of a particular age. Okay. And you know what I'm going to do? What are those ones that falls within? Please pay attention. What are those ones that fall within? You see 5, 6, 7, 8. Now I will base the weighted average on that. Please pay attention. I'm going to base the weight with the weighted average on that. That's why you have this. Look at that. Why do you say y5, y6, y7, y8, y9? Those are the values of the predator that fall within that fall within that are in the neighborhood of a particular point in the predator that I'm interested in. Is there any question about that? You can see 5, 6, 7, 8, 9. And what the kernel is going to do is to find the average. Okay, you can see there's no y1 up to y4. It's only y5, y6, y7, y8, y9, then divided by that. That is the way the kernel work. Now, if you understand the way the kernel work, I think I have one to show. Let me see. Okay, I want to explain the way. I'm going to use this guy now to explain the way the local polynomial work. Are you focusing on the board? I just show you the way the other one work. You know, I told you, if you take a look at this blue line, the blue one, that blue one is the true underlying function. Okay. Now, if you look at here, okay, the idea of a local polynomial, we actually use a window. Okay. Now, there's going to be a window that will slide across the data point. But I'm only interested in a window that's actually within the neighborhood. Okay, like right now, if you take a look at what I have here, you're actually going to see that what will determine the number of data points that I'm actually going to use for that neighborhood is what we call window length. Window length is the number of data points that I will use for estimation in that locality. I'm going to say that again. You have a locality. It's called a local polynomial, okay, which means you have each locality. But what determines the number of data points you're going to use in each locality, okay, is what we call the window length. Now, I'm going to show you something now. Window length is very close to bandwidth in kernel smoothing, but there's a difference between window length and bandwidth. The bandwidth actually measure how influential are the values that are nearby, the values of the response that are very close to the values of the period I'm talking about. But the window length is not talking about that. The window length is talking about what will be the size of the data that I'm actually going to use that fall within that neighborhood, the size, not the influence. Okay, now now what actually happened now in the local polynomial. Why is it called local polynomial? Because I'm still going to fit. I still need to decide on the polynomial of certain degree. Okay, I did not do that in the kernel smoothing. Does that make sense? But so it is called local polynomial, and that was why I said, okay, here in this picture now, I'm using a polynomial of degree 2 and with different window size. when I use a window size of 0.1, you know the meaning? When I just use 10% of the data within that locality, very close. So this is what I'm actually going to have. When I use window length of 0.5, when at time I could use twice, like a 200%. So what we observed the other time is still what is going to happen. Okay, the window length of 0.1, you see fluctuation, high variance, low bias. The window length of a 0.5 is the one that balance a trade-off between the bias and the variance, and the window length of 2 will show low variance but high bias. Okay, so that is how that really works. Okay, now this is when I'm trying to look at the different. You may want to see what is the difference between a piecewise polynomial and a local polynomial. A piecewise polynomial is parametric. Local polynomial is non-parametric. Piecewise, the two of them, the connection, let me tell you the connection between the two. In the two, they have a common parameter. You need to decide on the degree of polynomial to fit, whether for piecewise polynomial in parametric or for local polynomial in non-parametric. But let me tell you the difference. In the case of a local polynomial, you need a window length. You don't need a window length with piecewise polynomial. But with piecewise polynomial, you need a cutoff point. Does that make sense? Okay, so that is what I'm trying to explain here. Now, the third is what we call the smooth splines. Let me tell you this. The idea behind the smoothing spline is to mimic a natural spline. A natural spline is seen to be the best among the parametric. Why this smoothing spline is actually being designed to mimic the natural spline in the parametric. And I'm going to tell you the difference. Okay, now I want to welcome you to smoothing splines. Let me tell you this. When you talk, the smoothing spline is different from kernel smoothing. It's different from local. Why? Why is it different? Because the smoothing spline will fit the function over all the entire range of x. Local polynomial doesn't do that. Kernel doesn't do that. Does that make sense? Now, over the entire range of x. And when you do that over the entire range of x, okay, and that was why I said here, I said smoothing spline do not require the specification of knots or local window, because it's actually going to fit over the range or the entire range of x. And it will do that by minimizing. Of course, you all understand, you're all familiar with this guy. What is it called? That's a sum of square error, right? Sum of square error, right? Okay. Why are we using this? It's going to minimize the sum of. Why are we minimizing the sum of square error? Because we want the function, okay, to stay close to the data, to fit the data. Now, and that will be subject. This is the difference. Take a look at this. That is what is going to hard to be able to, control the smoothness. This is synonymous with what we did in regularization. You remember lasso regression, ridge regression? What do we add? We added a parameter to what? To sum of square regression. Sum of square error. Okay, we added a parameter, and that very parameter that was added is to penalize, for complexity. But here, the parameter we are adding is lambda integral the square of the second derivative. Why are we using the second derivative? I told you the other time. The second derivative will determine how rough a function is. And one of the advantages of natural spline, we set that second derivative to be equal to 0 at the boundary. Does that make sense? Here, we are adding lambda integral the square of the second derivative, okay? And if you take a look at what I said here, please pay attention. You don't understand, ask me question. Ask me question, you don't understand. I said the second derivative provide a measure of how rough the function is. We don't want it to be more rough. We don't want it to be maybe um, perfectly smooth. No, even though we want some smoothness, we don't want a perfect smoothness. Perfect smoothness is not good for interpretation. Does that make sense? So now, if you take a look at, and that is what I have. So the lambda here is the smoothness parameter that can be determined from the data. The lambda is the smoothness parameter. Okay. Now, and I said something here. I said specifically, the lower the second derivative, the smoother the curve. I told you, the lower the second derivative, the smoother the curve. And that was the reason why in the natural spline at the boundary north, we set the second derivative to 0. Okay, now, and that was why I said, for instance, a line has second derivative equal to 0. A line has second derivative equal to 0. Now I said the effect of the penalty parameter. So that lambda now is a penalty parameter for smoothing. It's a smoothing parameter. Okay. Now, if it is large, it has an effect. If it is small, it has an effect. Okay. Do you know that? How do we determine lambda? Okay. How do we actually determine lambda? Please, I need you to pay attention to what I'm doing here. You know, I said we are minimizing the sum of square error subject to that. You know, that was what we added. Okay, that was what we added to the sum of square error here. You see, that was what we added. And with the weight lambda, and I said something here. How is the lambda going to be chosen? We can use a cross validation to select lambda. And that was what I'm trying to say here. I said it can be shown that f resulting from the minimization problem in 5, that is when I have the sum of square error plus lambda integral, the second derivative of squared, okay, is a natural cubic spline with not that. So which means alternative approach to natural cubic spline is what? Is smoothing or is this? What that I'm actually smoothing spline that I'm discussing right now. Now I said we can, for a start, just like the same way we did under lasso and the rage, that we normally, try some values of lambda. You can see here, we're going to try some lambda from 0.1, 0.2, all the way, okay? And I said, for each value of the grade, we compute the cross-validated. And what are we going to use to choose the lambda? We use the one with the smallest test MSC. You remember what we did before? Okay, smallest test MSC. That's what we're going to choose. Now, I want to show you something now. When we now apply the smoothing spline on trying to figure out the relationship, the trend here between the wage and age, you can see what happened. Very smooth. Look at that. It's making sense. And this is synonymous with a natural spleen in a parametric. That is synonymous with natural spleen in a parametric. I want to see if I have something more to. Okay. Okay. So there's something I'm going to, like I said, lambda controls smoothness. When lambda is too small, I need you to write that down. When lambda is too small. Now, when lambda is too small, let's come here. Let's come back to the equation. When lambda is 0, what are you doing? When lambda is 0, you're doing nothing. Okay? You are not, your function is not likely going to be smooth at all when lambda is 0. So let's say if lambda is small, what happened? Okay? If the lambda is small, then you're actually going to have low bias and high variance. Can you write it down? When lambda is very small, of course, when lambda is very small, the whole thing will be very close to the sum of square error, right? When lambda is very small. Like if lambda is very close to 0, you more or less have equation 5. You more or less have this guy, which means the problem is still going to be there. The problem of high variance is still going to be there. Even though equation 5 is actually good because it's only going to be good for the data, for the training data. Equation 5 only going to be good for training data. The bias will be very low. Does that make sense? So which means when lambda is very small or 0, you are going to have high variance but low bias. But when lambda is very large, what happened? The reverse will be the case. Low variance, high bias. Therefore, we need to be able to use a cross validation to choose the optimal values of lambda that is going to work, that will enable us to balance our interpretability and smoothness. When I say interpretability and smoothness, so you understand what I mean. Now, I want to go to using the next 10 minutes. Okay, so I said here we expect the plot above to be similar to that of the natural cubic spleen. And that is because the minimization problem that we're trying to solve lead to a natural cubic spleen. But the advantage here is that we don't have to choose the number of knots. Okay, we don't have to choose the number of knots. And the only thing that determines flexibility is lambda here. The only thing that is called a smoothing parameter. Now, lastly today, I want to walk you through another model, all this why, when we look beyond linearity, we've been focusing on one predictor. Does that make sense? For instance, the one we just did, we only focus on age. What if in a situation where we want to look beyond linearity, but we have more than one predictor? Then we're going to make use of generalized additive models. Generalized. Now, in the generalized additive model, okay, you're first going to write the conventional multiple linear regression model. Take a look at this. But you know what we're going to do? Because we don't want a linear combination, because when you take a look at this guy, what do you have? In this guy, you have a beta naught, if I want to write it out, plus beta 1 x1, right? Okay, all the way, right? All the way, okay? So probably the beta PSP, but we don't want linear combination. Don't forget, we're actually looking beyond linearity. What are we going to do? Looking beyond linearity, then equation 6 will replace that. You know what we're going to do? What we're actually going to do, okay, each of these, we have their function. That we have f of x1. That will be a function for that. Okay. And that function is going to be a smooth function. That will be a function for all the combination. Okay. And that is what we call generalized additive. Please pay attention. That's what we call generalized additive. There's going to be a smooth function for each. So equation 6 is a generalized additive model. Does that make sense? I said we use generalized additive model for situation where the predictor is more than one. Okay? And I've shown you the equation, the model you have in equation 6. Now, why additive? Okay? Why additive? Because we're just considering the sum of the functions of the covariate, sum of the function of the covariate. We're assuming a function for the covariate, and we're adding them up. And that's why it's called additive. But you know the drawback? Oh my God. You know when you have more than one predator, there's possibility of interaction. Okay, it may be difficult for us here to investigate the multiplicative effects, such as interactions. But research are ongoing. I want to believe probably that problem, they're looking into the problem. Now, how do we, estimate parameter in a generalized additive model? If we want to estimate parameter in a generalized additive model, there's something I need you to pay attention to. Look at the model here. The model is this. Don't forget, the linear combination, we write it in terms of f of x. Beta 1 x1 will be f of x1, beta 2 x2 will be f of x2, and so on like that. Now, each function is going to be called a smooth function. And if it is a smooth function, I can use any of the method that I've used before. Local polynomial, spleen, and so on like that. I can use scanner. I can use local polynomial. I can use a piecewise polynomial. I can use a natural cubic spleen. I can use a cubic spleen on the function. And this is how you're going to, if you want to estimate that, this is not going to be part of my exam anyway. So it's just for information. Okay? Just for information. But if I want to estimate that, what am I going to do if I want to estimate parameter in a generalized additive model? I will first initialize, the beta naught and the FG. Of course, the estimate of the beta naught is the Y bar. And after getting that, I'm going to set that to 0. For this guide me for every J, we are f of 1 cap 0, f of 2 cap 0, f of 3 cap 0, and so on like that. When I do that, the next step is to compute a partial residual. Partial residual. What do I mean by partial residual? Okay, I need you to pay attention now. I've already obtained my beta naught cap. So it's going to be y minus beta naught cap, then minus the sum of the functions where k not equal to j. Then I will continue to do that. That is the algorithm until I get a result. I think my TA is going to walk you through how to do that. Now we update, and then finally we're actually going to get result. You can see I said that not in the exam. It's not going to be in the exam. So this is just for your information. For your information that we can also fit non-linear model for situation where predator is more than one. And you can decide when you're doing that in your smooth function, you can decide to use any of the method I've discussed today, either the one that fall in the parametric or the one that fall in the non-parametric. What is next? What is next? We are actually moving, gradually moving to another exam. And of course, just like what now that I've done with my lecture, not lecture for the semester, but up to midterm 2, it is time for me now to release the midterm 2 practice questions where I'm going to go over that with you. And of course, the exam will come eventually. So this is where I'm going to stop. All my videos are published up to date. So you can check the YouTube. You're actually going to see that. Is there any question for me before I go today? Any question? Go ahead. I think I updated. If you check the syllabus, what is the syllabus? Because I don't want it to also class with 5401, just like the way I did the other time. I need you to check the calendar in the syllabus. I think I changed something. Yeah, just check the calendar in the syllabus. Okay, so make sure you all stay safe and have a lovely weekend. Bye for now, everyone.